everyone, and welcome to Talk Nerdy. Today is Monday, February 6th, 2023, and I'm the host of the show, Cara Santa Maria. And as always, before we dive into this week's episode, I want to thank those of you who make Talk Nerdy possible each week, including my top patrons here on Patreon. They are Daniel Lang, David J.E. Smith, Mary Neva, Brian Holden, David Compton, Gabrielle F. Jaramillo Gonzalez, Joe Wilkinson, Pasquale Gelati, and Ulrika Hagman. If you'd like to pledge your support on an episodic basis and learn how you can get ad-free episodes, all you've got to do is visit patreon.com/Talk Nerdy. All right, so let's get into this week's show. I had the opportunity to sit down, again, remotely, always remotely, with Dr. Suzie Sheehy. She's a physicist, an academic, and a science communicator who divides her time between research groups at the University of Oxford and the University of Melbourne. And she's currently focused on developing new particle accelerators for applications in medicine. She has a new book, actually, it's her first book, called The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Changed the World. So without any further ado, please welcome to the show, Accelerator physicist, Dr. Suzie Sheehy. Well, Suzie, thank you so much for joining me today.
Thanks for having me. It's lovely to be here.
It is lovely. Are you in the UK or are you in Australia?
No, I'm in Australia at the moment. So it's just 9 a.m. here and it's going to be about 32 degrees Celsius. So we're expecting a hot one today.
Oh, wow. How funny. Okay, so it's 5 p.m. where I am because I'm on the east coast of the U.S. right now. And that is a big time. You are in the future. You're time traveling right now.
I'm on Saturday. Yeah.
It's so kind of you to be doing this with me on a Saturday. Thank you so much. So I'm super excited to talk about your new book, The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Changed the World. And not only are you a physicist, you're a particle physicist, right?
Yeah, technically a subset of that. I work on the machines themselves, the particle accelerators. So technically I'm an accelerator physicist, but yeah, that's within the general remit of particle physics, yeah.
You are definitely the first accelerator physicist that I think I've even met or spoken to. I've had some particle physicists, as friends or have had them on the show, but I don't think I've ever met somebody who is an accelerator physicist.
Yeah, I think there's fewer of us. But yeah, we sort of work right in the physics of the actual machines themselves and how beams behave and all the different ways of producing and manipulating beams of subatomic particles. So those particle physicists really need us because we're the ones who provide them with their experiments.
Absolutely. And so you've also worked for quite some time as a science communicator, doing what I and so many of my friends and colleagues and individuals who I've had on the show before do, translating these ideas to the public. Is this your first book?
Yeah, it is my first book. I've been doing science communication sort of originally alongside my studies and then alongside my research for many, many years. It's always been my sort of second professional strand, as it were. And this book has been a lovely deep dive into the history of my field, which has felt like those multiple strands have sort of come together. And so my academic life and research life and my science communication life are all heading in the same direction now, which is nice.
I love that. And so for all intents and purposes, you've been working on this book since you started your career, but I'm interested, how long has it been since you actually sat down to say, I'm writing a book now?
Yeah, so in the nonfiction world, it starts with the proposal stage. And it took me about 4 years after I met my agent to actually have the time and the right idea to sit down and write the proposal. And then when that happened, it was like 3 months from writing proposal to selling the book. And then it was about 18 months to write the whole thing because it required, as you might have gathered, reading it, like quite a lot of research back into the original papers and all the biographies and autobiographies. And of course, that 18 months just happened to coincide pretty much with all the COVID lockdowns. So I was shut out of my lab for most of that time, which is why I think I got it written.
I love this approach because it's one of these important aspects to science and our ability to communicate science is, I think, the history and systems of science. I guess I'm very lucky that my academic path, which started in neuroscience and now has like kind of ending up in clinical psychology, history and systems from an academic perspective is really emphasized and promoted. And I always noticed a huge difference between my training in biology and my training in psychology in terms of why do we know or how do we know what we know? I found that the psychology courses I took were so much more focused on, well, first this person did this, and then they realized that it was like this, and then it happened over here, and that's why we now know that this isn't really like this. Whereas in biology, oftentimes it went backward. It was like, this is what we know. So memorize that. And then later we can kind of figure out exactly why we know it.
Right.
And that always bummed me out.
Yeah, this backwards version of history where you take what we know now and then you look back and like, oh, well, 20 years ago, they were missing this piece of the story. And then you don't learn that trial and error sort of faulting trajectory through people tried X, Y, and Z and it didn't work. Or, for 50 years, people thought this was true, and then this key experiment showed that it wasn't. And I think in physics, we have exactly the same thing, and it bummed me out as well, which is we have this sort of, I call it the pigeon version of history. It's like this little version of history which is told in the reverse direction, as if we always knew that we were going to arrive at this point in understanding and just took a linear path towards it, when, as you know, that's not how science works at all, right?
Right, absolutely. And the truth of the matter is, not only is that not how science works, and so of course, learning how science works is important for learning the scientific method, but it's also like there's so much context missing when we think of science as a thing we're supposed to learn or a thing we're supposed to memorize instead of a process,
right,
where at any given time we have a snapshot of that process.
Yeah, I would completely agree with that it's really important that people understand that science isn't just a set of facts that we sort of go around and you sort of learn these facts or you learn how to solve some equations in my field. Instead, it's really this process of how we know what we know. And that's really what I wanted to highlight in digging into this story in the history of my field in physics. And one of the things I found when I delved into that research process is that even the stories I had in my head, which I thought were pretty accurate as to how sort of key experiments were done and key discoveries were made, was so simplified and so different to the reality. And it was really valuable to me as a researcher to understand that the experiences that I have when I go into the lab every day, which are often experiences of frustration, of feeling like I don't understand what this bit of experimental kit is doing, of having to work my way really slowly, or so it feels, through all the different steps to understand exactly what's happening, when often in physics, at least, you can't sort of see what's happening directly with your own eyes. And that actually has been a really common experience. And that the wonderful thing in my field is that those experiences have been built up over 120 years or so to all these wonderful discoveries that you just wouldn't think possible when you walk into the lab every day. And yet it's very heartening to me that despite all of our foibles and despite how difficult these things often feel, that we have discovered so much, and that at least in physics, because we can rely on physical systems at least being reproducible most of the time, we can build on that knowledge so effectively towards this huge understanding of how our universe works on a fundamental scale, that really it's really hard to understand how we got to this level of precise understanding without going back through that trajectory. And so it really surprised me in a way that kind of nobody's told that story, especially not through the experimental line. And so that's pretty much what I've tried to do.
I love it. And I'm excited to hear some of that story. But before we hear some of that foundational story that you mentioned about your field, I'd love to hear your own personal story about your journey within your field. So tell us a little bit about maybe when you first started becoming interested in math and physics. Were you young? Did it not happen until like further along in your academic career? And then sort of what did you study in school?
Yeah, right. So I was always fairly good at like maths and physics and sciences, but I was also pretty good at, just academically across the board. I was always an interested kid, so I took my schooling seriously. So when I finished high school and had to go to university, I was one of these kids who really struggled to choose what they wanted to do. And so I decided to keep my options open. And I actually started studying a double degree that you could do at that time in engineering and science. And I sort of thought, okay, here's the practical. The engineering is the practical. I know what that career would look like if I became a civil engineer. And, it's profession. And the science I kind of added because I thought, well, I've always been interested in this. A number of high school friends thought I was going to go and do musical theatre, by the way. They thought I was going to do
I love that.
acting and singing and dancing, which I used to do sort of for fun, but would never decide to do professionally. So you can see like my interests were quite varied. And then when I was studying at university, I write about this in the opening of the book, I had this wonderful experience where I met some friends through my physics courses that I was taking sort of for extra education on top of my engineering degree. And we went out to the bush with telescopes to this dark sky site, which is an area that's set aside where there's not too much like background light that interferes with astronomical viewing. And it's about 2 hours outside of Melbourne. There's quite a few of them in Australia because we have beautiful dark skies here. And we sort of lay down and just let our eyes adjust. It takes about 20 minutes for your eyes to adjust to see the stars properly above you. And it was just this complete perspective shift for me, because the night sky here is absolutely stunning. It's we look into the center of the Milky Way galaxy, whereas in the northern hemisphere you look outwards. So we actually have a much brighter band of stars across the center of our sky, which is actually the plane of the Milky Way galaxy. It's so bright actually that our indigenous astronomical traditions from Aboriginal and Torres Strait Islander peoples, they often have constellations based on the dark dust clouds within that bright band of stars rather than the stars themselves. Yeah, that's how bright it is on a proper dark night. And I just remember as sort of this huge constellation, or the Milky Way sort of moved across above me through the course of about an hour or so, and you could tell it was shifting. I had this huge shift in understanding that we were really just one species on the side of a planet, in this galaxy, and that there's billions of galaxies, and I just suddenly was like, oh God, everything I've studied and learned up until this point is so small compared to what's out there in the universe. And I felt just really inspired to just learn more at that point. That was my desire, was to try and understand a little bit more about how all this is put together and how it is that the same matter that makes up all this stuff I'm looking at out in the universe has also somehow created me and everyone around me, and even conscious beings themselves. Never quite solved that one, but I don't think humanity has, so I forgive myself there. But yeah, so I just really, I had this shift away from just wanting to use the results of research and science to, say, design bridges and buildings in engineering, and I really got much more interested in the questions that didn't have answers and in understanding those big questions.
Okay, so clearly you're sort of struck with this incredible awe, and you realize the direction that you want to go. But how do you logically make those leaps or take those steps to actually get into the logistics of doing what it is that you wanted to do?
Oh, so how did I adjust? So I eventually quit the engineering side of my degree and just finished the physics side. And I had a great mentor who actually taught me in my first year, and he's now one of my colleagues at the University of Melbourne. I studied my undergraduate here, and at some point I started seeking out research experiences. So I spent a summer doing a research project, which was the first time I got to use a particle accelerator, which was very fun, and led to my first publication, which came out a few years later. But I really started to get this experience of what it's like to do research. And so when I finished my degree, I guess I got quite serious about it. Like, I started putting a lot of work into understanding it, to getting good grades, so that when I completed my undergraduate degree, I knew I wanted to go on in research. And so at that point, I actually applied to Oxford in the UK. I have dual citizenship, so it was pretty easy to think of moving there. And yeah, so I actually moved to the UK for what turned out to be almost 15 years. So I did my PhD over there, and then had a research fellowship after that, and then slowly built up my own research group there for the first time. And I've only just now shifted back to Australia and sort of brought my research field home and started a new lab and a new group here. So it wasn't an easy trajectory. I mean, it sounds very linear, but it definitely didn't feel it at the time. It felt like I was just constantly pushing and pushing to try and stay in research and find the next job and produce the research and the publications that you need, because it's actually such a competitive industry.
And when we think about, I mean, maybe before I ask this question, we should take a step back and talk about what is an accelerator and what does it mean to be an accelerator physicist?
Yeah, sure. So in all these questions that are asked through the book about the nature of our universe, one of the key fundamental questions, right, is like, what is matter? What, when you pull it all apart, what is all the stuff around us made of? And of course, since ancient times, we've had the idea of atoms. So the idea that if you cut apart, say, even a grain of sand, then at some point you're going to get down to the smallest piece that was supposed to be uncuttable. That's what atoms actually mean. And then through various stories in the book and various experiments and theories, we discovered actually atoms are not uncuttable. There's actually things that are smaller than atoms. And what a particle accelerator is designed to do is to take these tiny particles, either the nuclei of atoms or other charged particles, and just give them energy, basically speed them up to a high speed. And that's fundamentally all that this machine does. But it does it in a very precise way, and nowadays in a very powerful way. And we are able to control the beams well enough to be able to narrow them down to less than the width of a hair and collide them head on around machines that are 27 kilometers in circumference. Here I'm talking about the Large Hadron Collider at CERN. And that is a huge challenge, to control billions of particles at the same time moving near the speed of light. I mean, you've got all sorts of electric and magnetic forces going on because particle beams are electrically charged. And if you remember back to, like charges repel each other, right? So actually the beam's trying to break itself apart all the time. So the job of someone like me, the accelerator physicist, is to design systems that do all of those different parts of the process. So whether that's generating beams to start with, giving them energy using electric and magnetic fields, controlling the beams, usually using magnets, and then all the sort of higher order fancy nonlinear effects that we love in physics all come into play. So people sometimes imagine, if there's a movie version of a particle accelerator, which there have been a few, you sort of get this image of it like, okay, it's sort of some big machine with this laser beam coming through it. But a real particle beam is much more sort of unruly than a laser beam. I like to tell people to imagine a galaxy forming, swirling masses of stars. Well, imagine those stars are particles, and we're trying to form that galaxy and shoot it along at the speed of light within a machine here on Earth. That's kind of my job. That's what I try to do in the systems that we design. And the lovely thing about these machines is that they're not just confined to the realms of, high energy physics for a few elite researchers. As we've developed these machines and we've reached higher and higher energies with them, which typically means they get larger and larger, we've also found lots of practical applications for them. So today there's about 50,000 of these machines in the world, and about half of them
wow.
I know, it's a surprising number.
I didn't realize that. Yeah. Because it's true. Everybody thinks of CERN, and they're like, there's one.
But nobody thinks of their local hospital, which is where their local one almost certainly is.
Right.
Yeah. So, and nowadays one of the things I love now about working in this field is I can work on the next big particle physics collider, or I can work on improving the quality of cancer treatment using these machines, because that's what they're used for in most hospitals. And I just think that's a wonderful field to work in, to be able to have that curiosity-driven aspect and that applied aspect, and to just be able to choose at any given point which projects I'm working on, sometimes both. So yeah, it's I love that duality of purpose in a way.
Absolutely. So I want to ask some like specific questions here. Like when we talk about an accelerator, I envision some sort of tube-like structure that's maybe in a loop, but maybe not in a loop. And then you mentioned the beam, and you're right. I think when we think of beam, our head goes to laser beam. And so we go to this idea of like visible light or something like that. But when we talk about a beam within a particle accelerator, sometimes you'll hear the term thrown around like proton beam, but it's not always just protons, is it? Like what is the actual beam itself?
Yeah, so the beam is really composed of fundamental particles, so either or subatomic particles. So yeah, protons is one type that we can use. Or we can use other types of charged particles, and they do have to be charged. So electron beams is a very, very common one. Those are the ones that are mostly in hospitals. But you can create beams of heavier particles as well. Basically take any atom and strip some electrons off so it's charged, and you can accelerate that. We can't accelerate things like molecules, because the energies that we're working at would break the bonds between the atoms in the molecules. But we can accelerate basically anything that's a bit more fundamental than that. We can even accelerate now beams that are radioactive, so beams that actually decay while they're accelerated.
Okay, yeah, that was so. So a couple things come up when you mentioned that. So, and obviously, I am not a physicist, and probably some of the people listening also are not physicists. But when you take something fundamental like a subatomic particle, whether you mention any sort of charged particle that is stripped off or stripped out from the atom, does the process of accelerating it change its fundamental nature? Does it turn it into something else? Does it decharge it? Does it force it to bind or unbind from anything else?
No, not the process of acceleration. So all you're doing there is you have this sort of fundamental thing, say a proton. It has its natural charge, plus one charge in units of electric charge, and it has its mass. And all you're doing is giving it energy. That's pretty much the only thing. Yeah, as I said, some particles which are naturally radioactive, they may change form, but they were going to do that anyway, right?
Right.
Yeah, and the other thing, we had this question before of the visualization of the beam, and I think where we think about laser beams, that's sort of a visible light, right? But these particle beams are invisible to us usually. So also along this machine, which usually is a sort of tube-like structure with magnets and sort of little sections that impart energy to the beam, there's also a whole bunch of what we call beam diagnostics, which you can put in the way of the beam or interact somehow to actually give us a picture of what that beam is doing as it travels along, because usually it's invisible. We can't just watch it. So that's part of the job as well. That's the difficulty of actually being able to tell what's happening with all of this stuff, which is just so small it's invisible to us in any way. And that's actually been one of the fascinating things about the field, is we've learned all of this stuff about matter, but all of the things we're looking at are very counterintuitive, because we can't even sense that they're there usually.
Of course. And I mean, A, because they're so small, we can't see them, but B, because they are fundamental to everything. And I mean, that leads me to another really silly logistical question.
Oh, please do. Like, I'm enjoying the logistical questions.
Atoms are literally everywhere. They make up literally everything. How do you get the stuff to make the beam? Like, where is your source material?
That is a very good question that not many people think to ask. So it depends on which type of beam. So electrons are really easy. Okay. So if you just heat up a piece of metal with a current, electrons just start jumping out through a process called thermionic emission. And we actually cover this in the book. After the electron is discovered, just a couple of years later, the discoverer of that, J.J. Thomson, he describes this process of electrons jumping out of metals and into vacuum, pretty much. And that actually became the key piece of knowledge behind our understanding of how to make valves for the original electronics industry, so amplifiers and things like that, which gave us telecommunications and radio and the sort of music amplifiers, so rock and roll could come about. Like, it's actually an incredible amount of stuff that came from understanding just literally how electrons jump out of metals. But that's exactly what we would use for the most part in an electron accelerator. Sometimes we get them out by hitting a piece of metal with a laser, and that just creates like a much more controlled or smaller beam. For protons, though, it's much more difficult. So what you do there is you start with a gas usually, and in the case of protons, you'd start with hydrogen gas, because the hydrogen atom just has one proton and it has one electron around the outside. And those are electrically attracted to each other, right? So if you apply a very strong voltage to hydrogen gas, the electrons will go one way and the protons will go the other way. And if it's a strong enough pull, you will rip the electrons and the protons apart. The electrons will go out one direction, the protons will go out the other direction. And that's literally how we get a proton beam. So at the start of the Large Hadron Collider, I like to sort of show people this photograph. Usually it's this little tiny bottle, you know, the small size gas bottles, little tiny bottle of hydrogen gas that provides all the protons that have ever been used in the Large Hadron Collider. And that's literally the start of the process. It's a bottle of hydrogen gas.
That's what I was going to ask you. Like, do you bottle them? And how do you know that you've stripped the protons and the electrons apart?
Oh, so...
Are you accelerating them or heating them up in the machine already?
Yeah, so you do both. You actually heat it up and then you apply a voltage which sort of accelerates them in a particular direction. And then you've got electrodes to focus them and things like this as well. So yeah, it's all happening at once. But because if you apply that voltage, because of the different charge, because electrons are negative and protons are positive, they'll literally just go in opposite directions. So you don't get too much contamination, as it were. And even if you did, again, if you put those through a magnet, a negatively charged particle will bend in one direction and a positively charged particle will bend in the other direction.
Right.
So you can separate things out pretty easily, and even you can separate things out based on their mass as well. So we've got all these techniques, right, based on mostly electricity and magnetism, to sort of separate things out and make sure that what we've got in that machine is a pure proton beam.
I love it. It's basically like electrical and magnetic sieves.
Yeah, that's a good description.
Because I think we can think of these things in mechanical terms because we use them, right? Like in a kitchen, you're using cheesecloth, or you're using like a screen to filter things, or you're powdering your sugar or something like that. Some things fall through, some things stay up at the top. And you're kind of doing something similar, but you're using much more sophisticated and specific tools.
I like this idea of so it's called an ion source, the device that does this. I like the idea of an ion source as like a very fancy cheesecloth.
Right, yeah. Like, this is how my brain works. I love that. Okay, that's fascinating. Okay, so now you have the stuff. You have the it's not really goo. It's just, well, it is stuff. It's just ineffable stuff. It's effable for you, but for us, we can't see it or touch it or feel it or taste it. But of course, the question that I'm sure a million people have asked you, what happened? Like, you don't want to be in that thing. Well, that would screw up the experiment. But even if it didn't screw up the experiment, like what would happen if that beam passed through you?
Oh, people love asking this one. Yeah. So first of all, I should be really clear that like all of that, after that initial stage of the gas being ripped apart, everything has to happen under high vacuum. So all the air and gases have to be pulled out by vacuum pumps, because otherwise...
Oh, right. So you die in there anyway.
Well, yeah. If you could get in there, and the beam pipe is usually only a few centimeters across, if you could get in there, you would suffocate to start with, and then all of the water and everything would be ripped out of your body by the vacuum. It wouldn't be very pleasant. So don't do that. Yeah. But yeah, so everything happens under a high vacuum, because otherwise these very tiny proton beams would have a chance of scattering off of gas molecules and getting lost. And once you have a lot of energy in a beam, that can actually be quite a dangerous thing. If enough of those particles get lost, for example, in the Large Hadron Collider, you only need to lose about 1 in a million particles before you are melting a hole in the side of the beam pipe, which is really dangerous. So these things actually together contain a lot of energy. So everything happens under vacuum. And then one of the questions always is, okay, what if I was to stick my hand in the way of the Large Hadron Collider beam, or your head in the way of the Large Hadron Collider beam? And at those very high energies, believe it or not, high energy beams interact less in human tissue than lower energy beams. It's sort of counterintuitive.
Okay.
But there's so many particles and so much energy in the LHC beams that I once did a calculation of this, and I had to make some assumptions about like the beam recirculating through your head 10,000 times, something like that. And I think I calculated that the radiation dose, I didn't calculate the heat deposition, but the radiation dose would kill you. I think it was 78,000 times over.
Oh no. So it's basically
so
like being in a detonation. Like it's not, I mean, you're not going to explode, but the dosage of radiation that you're going to get is like being at ground zero. Like you don't want that.
Yeah. I guess the difference
like
though is it's like a very specific, very small deposition of that. So rather than, and that's the one thing that actually we don't know, obviously, because we've never done the experiment of putting someone in a beam of that kind of energy. But there was this guy in the late 1970s, I think it was. His name's Anatoly Bogovsky. He was a Russian physicist who was working on a machine quite a bit smaller than the Large Hadron Collider. And he was doing some maintenance one day and he stuck his head in the beam. He thought it was off, obviously, and health and safety was not such a big thing back then. And he accidentally stuck his head in, I think it was an 80 giga electron volt beam, if that means anything to anyone in your audience. So to me, that's quite a high energy beam, but it's not as high as the Large Hadron Collider. And the beam like went through his head and out the other side, and he reported seeing a flash as bright as 1,000 suns. And astonishingly, he didn't die. It paralyzed one side of his face, and I believe he also it would have had impacts in his brain, and so he had, I'm not sure if it was schizophrenia, but he certainly had personality changes afterwards.
Okay.
But he actually went on to work for many years at that facility in Russia and complete his PhD, and had a long life. And interviewers went to see him many years after the accident and was surprised to find that like the side of his face that was affected by the beam was sort of preserved at that moment in time, not because there's any sort of Botox effect, but because literally that side of his face was paralyzed from the radiation. And so he never developed wrinkles on that side of his face because he didn't move his face.
Right. How fun. Oh, wow. But no brain cancer or anything. No fallout from the radiation later.
Not that I've heard of. I haven't seen a follow-up article for a while, which is interesting. But anyway, so that's the slightly crazy don't do that effects of
don't do that. Don't do that.
But we do. I mean, some of what I work on now is intentionally using beams of charged particles at slightly lower energies and at much lower intensities of radiation to intentionally treat tumors in people's bodies. So that's either using X-rays generated using a beam or directly using particles like protons, which are now one of the most precise forms of cancer treatment. So part of what I do is design next generation machines for that form of cancer treatment. So anything that can have that sort of negative effect, as it were, if you learn to control it well enough, you can use it to our advantage when you need to actually do sort of almost precise surgical radiation deposition inside the body. So we do that. That's one of the uses of accelerators now.
Yeah, and as you mentioned before, it contributes to the number of accelerators that are on the planet today. Yeah,
exactly. One of the interesting research projects I work on at the moment, and we've gone way off track with the book, but this one is in the book, is one of the things that I guess I spent 15 years of my career working in this field of this high technology being used in medicine. And I guess there was always like this big elephant in the room of like, well, yeah, it's used in medicine where people can afford it and where it's accessible, right? But it's not equitably accessible around the world. And so one of the projects I got involved in starting in about 2016 was addressing the issues that people were facing with using this high-tech cancer treatment technology called radiotherapy in low and middle income countries. And that, finally feels like I sort of got involved in a project which is like, okay, this is more the democratization of particle accelerated technology for cancer treatment. Because by 2035, something like 70% of all cancer cases are going to be in low and middle income countries. And the technology is failing there. It breaks down more often. It's hard to fix. It's not well suited to those environments at the moment. So it's been a lovely thing to get involved in. Completely different from my usual physics, much more socioeconomic factors and complex systems. But it's been, it's sort of close to my heart, that project.
There's just so many questions. Like, this is just so fascinating. I want to get to some of the stories in the book. You've pointed to a couple, but I definitely want to get deeper into some of the stories. But I guess the other question that is kind of out in the forefront for me is when people think of accelerators, they think of particle accelerators. It's in the title, you are an accelerator physicist. These are accelerators. It's all about, as you said, adding energy and accelerating these things. But very often we use the term like smashing particles.
Mm-hmm.
Smash some particles and see what happens. Are we smashing? Are we just making them go real fast? Are they going really fast until they hit something? Like, what's the
all of those things can happen. Yeah, so it depends on the machines. So the ones I was just talking about where we treat cancer, yep, you're accelerating them, you're pulling them out of the machine, and then you're smashing them into something, in that case a human body, right? Or some cancer cells in the human body. In big particle physics experiments that we have now, it's a much more efficient use of the energy that you've put into those particles if you actually smash them head on together, because instead of a whole lot of debris and energy sort of going off after the collision, in the head-on collision, you can take sort of all the energy in the system and put it into that collision. Now, one of the things that people find slightly difficult to understand is we're not just sort of taking things and smashing them like a child would with like a toy train or something, right? Like right. Smash it together, the wheels come off, the engine comes out, and there's some seats, and we piece together what a train looks like from this naive view of the pieces that come out. No, instead now, once you reach a high enough energy regime like we do now, we're just using these things as like bundles of energy from which to create new particles. And a friend of mine used to describe this quite nicely as, instead of smashing apples and getting out like pips and bits of apple, it's like we're smashing apples together and getting out 3 bananas and a mango. Right. Something completely different comes out from what was there before. And that's how we learn about the rules of the different forces and the creation of these different particles in the universe and how they all fit together. We're no longer just looking at what is physically inside the center of an atom, for example. We are trying to create things that otherwise don't exist in nature. But they are a part of nature. They're just hard to make.
Right. Can you tell me, when we see the images coming from places like the LHC that look like the little explosions with all the little squiggly lines going off in different directions, is that a visualization or is that an actual image of something that we can't see?
So that's definitely a visualization.
Okay.
So what happens around that collision point, they put all these layers of detector, of different types of electronic detector usually now. And it's like the layers of an onion. It's like a cylinder, and these layers of detectors sit around it like an onion. And as these collisions happen, and then it's not just one or two particles that come out, right? Like all this gump comes out flying in all different directions, and they want to catch all of those things and detect them so they can piece together exactly what happened at the center of that collision. And so you've got to pick up all of those little things. So imagine pieces of a digital camera, but like thousands and thousands of them layered around in rings around this central collision point. And then as these particles fly out from the center, as they travel through the sort of sensors of the digital camera, they'll leave like a little dot. And so those traces that you see are basically those joining together of those little dots that traces out the tracks of the particles as they come out of the collision and allows us to trace them back to the collision point at the middle. And they're quite clever, these different layers of detector. They have different roles. So some of them are there just for like really precise position measurement. Some of them will measure charge. Some of them will measure the mass or the sort of momentum of the particles. And some of them are sensitive to different type of particles, because we have some that don't travel very far at all because they stop really easily. And then we have some, for example, particles called muons are famous for just sort of flying out of the detector and not being seen by anything. So around the outside, there are these so-called muon chambers, which do a better job at picking up those ones so that they don't get lost in the experiment. So basically, then we're counting up, and this is why we have so much data, right? This is why the data challenge is so difficult, because you have, I think the Atlas detector, which is one of the 4 main ones on the Large Hadron Collider, it's technically only a 40 million pixel detector, so like 40 megapixels, which doesn't sound much even compared to our usual cameras, but it takes photographs like so frequently and there's so much data in each of those pictures, right? So it just adds up over time to try and gather all this data and then sift through it and pretty much get rid of all the stuff we know about already. So there's a whole lot of filters that actually chuck out so much data that we know and understand already. And what they're looking for in that is basically something that they don't understand. They're looking for something that looks funny and makes them go, why is that particle behaving that way? But nowadays that's all done with, big computing systems, algorithms, like it's a really complex process. And there's like this experiment, the Atlas experiment alone, has about 2,000 physicists working on it. So these are huge collaborative enterprises now to try and sift through this data. But those same 2,000 scientists also contribute to the design, operation, and building of their experiment in the first place. So yeah, I've brought us straight up to modern day. That's how we do it now.
I love it. Okay, so last kind of like I don't know what I'm talking about question before we get into some of these stories. Okay, so before, when we were talking about these, like let's say a proton beam or an electron beam, these subatomic particles flying through an accelerator, you're adding energy to the system. So they are fundamentally what they still are. They're just very, very energized. But when we smash them together, and these filters, these different sensors and sensors are like showing us all of the stuff that flies away. Is the stuff that flies away, these component parts, these subatomic parts, fundamentally different than the proton? So they're like subatomic parts. Are they fundamentally different than the like protons or electrons that we're smashing? Like obviously, is there a gestalt here? Like is the whole greater than the sum of the parts? I guess is the question.
Yeah. So they are. I mean, I guess you could create protons, but protons themselves have particles inside them called quarks. And so often you get these sort of, they're actually called, technically, they're called jets. But you get these quarks sort of flying out and leaving these big tracks in detectors, which we refer to as jets. But those quarks need not be the same ones as went into the collision in the proton, in the proton originally. So it really is just like, imagine you just take all this energy, you mush it together, and then out of that, using Einstein's E equals mc squared, you can take all that energy, and with a pretty rubbish exchange rate, which is c squared, you can get sort of mass or new particles out of that. It has to obey a certain number of rules according to quantum mechanics. So for example, like the overall energy in the collision has to be conserved. And there's other things like electric charge is conserved as well in that collision. So if you have, yeah. So there's some rules to the game.
And so that's how you know something's wrong, if you like add it all back up together and it's off.
Well, there's two things I can tell you if you add it all back up together and it seems to be off. One is, that something's gone wrong. But the other option is that something has been created that you haven't detected or that you don't recognize. And that could lead you to discovering something new. So
so sometimes you are looking for that.
Right, exactly.
Cool.
They literally call that missing energy. It's literally one of the things that they look for as a signature in the experiments.
I love it because I feel like sometimes when I ask the right questions and I get these really brilliant answers, and then I'm told about some of these very in the know, Yeah, it's missing energy. It's like, that makes sense. That's what I would call it too.
Right. We're very literal sometimes. Like that's
so great. I love it. Amazing. Okay, so I want to know, because of course the book doesn't just talk about the beginnings of the accelerators, but all the things that went into needing to get to the beginnings of accelerators. So I don't even know where to start with such a big history and such little time that we have, but I would love to hear maybe a little bit about like the first time somebody was like, yeah, we can do this. Because I've heard all sorts of stories like, literally, if we build an accelerator, we're going to produce a black hole and suck ourselves into ourselves. Like, there are some wild theories out there about what would happen if we did this, but we've been successfully doing it for some time now.
Yeah, so let me give you a bit of the backstory there. So the book actually starts in around 1900, the turn into the 20th century. And at that point, people sort of thought that physics was done.
Isn't that hilarious?
I know, right? Our biases. So they knew about gravity, they knew about electromagnetism, but they didn't know that the atom had a nucleus even. So there was no nuclear forces, which now we know make up two of the four main forces in nature, really. So that's a pretty big oversight. So we couldn't explain things like how the sun shone. There was no understanding of the fundamental nature of matter. And what happened in the early 1900s was a series of experiments and discoveries which sort of completely revolutionized that idea. So first of all, we find that there's the electron, which is smaller than an atom. And this takes a while to be accepted that there is something smaller than an atom. And then after that, we find that inside the atom, there's this really hard, dense nucleus, which consists of most of the mass of the atom. And so suddenly it's like, oh, wait, the atom is now suddenly mostly empty space with this tiny nucleus at the middle and these electrons like way, way out on the edges. And then as they start to understand radioactivity, so this idea that some materials or some atoms sort of give out or radiate other things, so whether that's a form of light in gamma rays or whether they spit out other particles, we then come to understand that radiation is actually atoms transforming from one type into another. So there's this huge overhaul in our idea of how the fundamental nature of matter works. And now you have to think of it as not just mostly empty and able to change from one form into another, but then quantum mechanics comes along as an idea. And then you have to start thinking of matter as particles and waves at the same time. And so people's ideas of just how the universe worked changed very dramatically. But then let me get to how particle accelerators came into the picture. First of all, they discovered that there's all this radiation raining down from space in the form of so-called cosmic rays, very high energy particles coming down. And this is what was used in the early days to understand and discover new types of particles. Or in the lab, they would use a radioactive source from some kind of mineral dug up from the earth. But both of those sources eventually sort of ran out of oomph and they couldn't discover more with them because the cosmic rays are very dispersed, right? There's a lot of them, but they're over a very large area. It's very hard to do a predictable experiment with them. And then in the lab, same thing. You've got this small radioactive source. It decays away over time, so it gets less useful over time. But the particles that come out of a radioactive source spray everywhere as well. So if you actually want them to direct them in a straight line or do something useful with them in a very measured, laboratory controlled way, then it became very, very difficult to do that. And experiments would take a long, long time. And also, all of these sources, you have no control over how many particles you're working with or the energy of those particles. And so in the late 1920s, there was this race to build a device which could control and deliver beams of these particles with energies beyond what could happen in the lab already, and in a more controlled way than was raining down on them from space. And so that was literally the demand for a particle accelerator. And those early attempts were quite fascinating. And even until I wrote this book, I didn't know about some of them. So they would find anything they could get with a high voltage at first. because when you put a charged particle through a voltage, it gains energy. That's the basic idea. And so there were people working with Tesla coils, which create this huge, quite dangerous sparks, but they were trying to harness that to accelerate particles. I don't think that ever properly worked because they're pretty unpredictable. There were some researchers in Germany trying to harness lightning for the same means. And their experiment unfortunately ended not because one of them got struck by lightning, but because one of them actually slipped and fell down the ravine where they had mounted their big experiment with these like wires hanging over a ravine. So they were unsuccessful as well. And then other people started using big electrical devices, transformers, and things like that to try and build up voltages so that they could just put these beams through it. And the first people who successfully did that in a way that they could use the beam and split the atom was John Cockcroft and Ernest Walton, working in Cambridge in the Cavendish Laboratory in the UK, Cambridge, I should say. And in 1932, they managed to get a proton beam, and in this like really difficult to control device where they had all these glass cylinders which were sealed up with Bank of England sealing wax and these high voltages which terrified them, and the whole thing would like hum with this high voltage, and they controlled this beam as it came down vertically through this tube. It gained a bit of energy, and then they smashed it into a target of lithium, which is a type of metal. And using that, they saw then that coming off that, they could detect all of these alpha particles or helium nuclei. And so for the first time, they'd managed intentionally to take a beam, smash it into an atom of lithium, and then that split apart into two different particles or helium nuclei. And with that, they knew for the first time that they had split the atom.
Oh,
So
cool.
that's kind of the big backstory.
Yeah, so it was like a proof of concept, but in proof of concept that this tool can do this thing that's so important. We've been looking for a tool for us to be able to harness this. They also discovered a lot of things. Like, what was their ultimate goal? Their ultimate goal was to just be like, we need to make something that can do this, right?
That was the driving force behind it, was we need to make something that can do this. But their ultimate goal was to try and really understand the nucleus of the atom. And to do that, that's why they had to sort of get into the nucleus by bombarding this metal lithium with these high energy protons, and sort of by doing that sort of figure out what would happen. And what happens is actually you get to the point where you can split the atom, where you can really get in and understand how the atom is composed and the different forces holding together the atom. But over time, more and more different larger accelerators were built, and over time they start discovering all sorts of new particles. And so in about the 1940s, really this technology, these accelerators, took over the field as the technology of choice, because suddenly, you could smash a beam into a target, and the smashing beams into each other only happened later because it was much more difficult. But they were smashing beams into targets, and then suddenly they weren't just producing things that they knew about, like helium nuclei, but they were producing other types of particles which they didn't understand, which at first were called strange particles. Great name.
Yep.
and then over, like, by the time you get to the 1950s and even early 1960s, they discovered about 200 different types of particles, which we refer to as the particle zoo. And so it was this mad time of discovery where these machines got bigger and bigger. Suddenly you'd have to join together with all the other people in your country or in your area to work together in this large facility instead of having your own small lab at your university. And just the discoveries were unprecedented. But then, of course, at some point they had to make sense of all of this, right? It's like, how are all these particles related to one another? Why are there 200 different particles in nature when only a couple of them make up our everyday matter? Like, all of this stuff was well beyond our everyday experience and didn't seem to be necessary to our daily experience. So why do all these particles exist? And that was where eventually they pulled all of these ideas together into what we now call the standard model of particle physics, which is this beautiful theory that, from a mathematical perspective, explains how all these particles come about and what they're composed of and the forces that operate between them. And that is the wonderful journey that happened through this sort of 120-year adventure is that we managed to understand in really, one of the most predictive theories out there. This thing is accurate to like 1 part in a billion. And there is basically no other scientific field that can claim anywhere near that. In a psychology experiment, you're lucky if you can reproduce the experiment at all, whereas we can reproduce
exactly.
it.
Yeah, there's just way too much variance in that system, that's for sure.
Whereas we can reproduce these things and predict them to an accuracy, to 9 decimal places. It's incredibly impressive. And so that's kind of where we got to in around the 1970s and 1980s, where they sort of found the missing pieces of those. And then there was this one outstanding piece called the Higgs boson, which in the theory sort of gives everything else a mass, as it were, all the other matter particles a mass. And that took about 50 years to find. It was first predicted in 1964 by 3 different theorists. And then eventually it took until 2012 when that particle was discovered at the Large Hadron Collider. And so we almost get to this point, which is resonant with the turn of into the 20th century, where it feels like the story might almost be done, right? But I don't want to give the impression but there's a big but coming to that. But what we've discovered in the meantime from things like astrophysics and cosmology and other measurements is that all of this stuff that we've discovered in this beautiful theory, first of all, the theory doesn't take gravity into account. That's quite a large oversight that we can't combine these wonderful theories of quantum mechanics and all this stuff about particles with our theories of gravity at the moment. So that's a huge outstanding piece. And then the other thing that's really intriguing is we now know from experiments that all this matter only makes up about 4 or 5% of the total mass energy content of the universe. So we know that out there is way, way more. There's something called dark matter, and even more obscure, something called dark energy. And I feel like that's where a lot of people are focused at the moment, is trying to go beyond what we now know and into this, like the other 95% of the universe. So it's just, I know it feels like a never-ending journey, and it is, and we've come so far, and yet there is so much more out there to discover. So we are in no means done with physics yet.
But that's why it's so exciting. And I have to say, like, one of the things that I love about the story that you tell is this thing that you see so often in science, and you see it so beautifully in this story about accelerator physics, but you also see it beautifully across many other fields of science, which is, let's see, how can I put this? Very often, I think we're left with, in the textbooks and in the sort of lore, the wisdom, the thing we know. This is some sort of rule, or this is some sort of behavior, or this is some sort of label that we have for this thing that we know. And like we talked about before, how do we get to the thing that we know? Well, in order to get to the thing that we know, we need tools. We need very often inventions. We need machines or calculations or means by which we can get to the thing we know. But I think what's often missing from the equation is that you can't extricate the knowledge from the tool. They're in lockstep with each other. And so many things we know, we only know because we were like, I can't move forward without building a thing to help me move forward. And then we build the thing, and then we know all this new stuff, and then we need to build a new thing. And it's so cool that so much of science works that way.
I completely agree. And, one of my key points of this book really is to highlight the fact that sort of how we know these things is just as important as what we know, if not more so, actually. And the how is just so much more interesting in terms of the human stories, in terms of that driving forward of technology, in terms of even the psychological and societal aspect of this drive that we have to know things about our world. And that's where in the subtitle, this, change the world aspect comes from, because what I've tried to tell in each of these experiments is the so what, so what, other than understanding physics, what became of all of this? And I gave the example earlier of the entire electronics industry, which is a pretty important one.
Right, yeah.
And we've heard about some medical technologies, but there's so much more than that. Even the World Wide Web was invented at CERN by a British scientist called Tim Berners-Lee when he was trying to solve the data handling issues that CERN was going to have when their new collider started up. And that's why he invented the protocols of HTTP and HTML and things like this to try and share, so that scientists around the world could share their data. And that got added to the sort of back end aspects of the internet and created the World Wide Web that obviously we know and love. And it's incredibly difficult to sort of put a value, right, on what the web has done for us. So that's just one example of the sort of almost serendipitous technologies and ideas that can come out of really sitting at this cutting edge in terms of science discovery and technology. And it's a really exciting place to be, and it has given us so much of our modern technology already. And it's not the reason for doing it. It's kind of a byproduct. But it's what was important to me is to explain that this process we go through of trying to understand really difficult things has byproducts, right? It's not just, it is a cultural activity, but it's not just a cultural activity. It can go beyond that.
Absolutely. Gosh, there's so much more we could get into. I've kept you for so long. I always ask my guests some closing questions. I ask them all the same 2 closing questions, and I want to get to those. But before I do, I was wondering, Suzie, like as you were doing your research for this book, is there anything in particular that you came across that you haven't shared with us? Because I know we meandered quite a bit. We got back to some core components. We also got back off on some tangents. But was there anything like wow moments of discovery or just curiosities or interesting things that you came across that you feel like might whet people's appetite a little bit to continue and want to dig more into the book?
Yeah, the one thing I absolutely have to share is that what really jumped out of me in the research in this book was the stories of women. Often women who I hadn't heard about before, even though I'm a female physicist and I'm obviously tuned to look for these stories. And yet, as I went through the original research papers, looked at the photographs, read the autobiographies, and I found all these references to women whom some of whom I didn't know before. And so what I've worked to do in this story is to actually reintegrate those stories of women and put them back in their rightful place in history, because there is this tendency or this effect to sort of write them out of the history, often because their careers ended earlier than they ought to have done. Usually because they've gotten married and had children, and then they, at that time, up until about the 1960s and 70s, actually, women were forced to quit their job at that point. So even if they were there working in the labs, they would have to quit. And this happens to at least one of the women in the story. But other than that, their contributions and their discoveries and their inventions, there is this sort of systematic thing. It's called the Matilda effect, whereby their contributions are often overlooked or ignored, not recorded, or even attributed to their male colleagues or spouses. And this is a systematic thing that has happened. And so it's really important that we bring those stories back into the main stories of the history of physics. And so that's one of the things that I've tried to do where the information was available, although often the information was simply not recorded. So that's been a wonderful thing for me as a modern female physicist to look back on my field. And it's just, even in researching and writing the story, it was so clear to me that like there was this white man narrative, of the history of physics. And so it has been such a wonderful thing to at least find women, and not there's at least one woman of color as well who I found in there, and wrote her story back into her rightful place. And they don't normally get celebrated in that way because they weren't awarded the Nobel Prize for obvious reasons. And so that really was, I think, the biggest thing that I discovered was that these women have been in my field all along and have been making wonderful contributions, and that the fact that we don't have more stories of that is because we've been keeping people out and keeping out their contributions from science. And so I think that's also another aspect which I think is really important, is to learn culturally how to stop pushing people out of these kinds of field of research. And yeah, just including the stories of people who went before is one of those ways.
Oh, I am so grateful to you for this. I'm so grateful to you for sharing those stories with us and kind of reauthoring some of these things and I love the way that you phrase that so beautifully that these aren't people who like didn't make their way in. They're people who are systematically kept out. And it's so important that we see that there were active and passive, overt and kind of covert forces at work that prevented these individuals who were so fundamental to these discoveries from basically getting any credit for the amount of work that they put in. So
yeah, exactly. And even their biographies and things, a lot of them were only written since about 1990. So I was grateful at least to the other, especially to the proper historians, because I'm not one, who actually went in and did that work, because there's very little source material, especially if these women have passed away, because they didn't have their biographies written, they weren't interviewed, their diaries weren't kept because they weren't as celebrated as their male contemporaries.
Right. And then their names were left off of publications. Like they were, actively removed from, or very often, I'm assuming you came across this as well, because I've definitely seen this, where when women were systematically disallowed from having certain ranks and titles and positions, they would do the same work as that rank, title, and position, but they wouldn't be credited with it because they were a, quote, assistant.
Yeah. And they do it unpaid. There's many, many stories of unpaid women working in the sciences, which is also interesting socioeconomically, because that means that only the richest, the women who come from rich families can do it. So even the stories we have are not always,
true. There's a certain amount of privilege. Yeah, that's for sure. Well, it's just fascinating. I mean, so much more that we could dive into, but of course it's your weekend and I can't keep you from your weekend. But can I ask you, I do close my show by asking my guests the same two questions. So they're kind of big picture questions, and I'm always curious about their responses because I'm so lucky on Talk Nerdy to have had so many guests from so many different walks of life and so many different fields of science. So here they go. I want you to think about the future. And your future thoughts may be very different from my own because they could be in any context: personal, vocational, communal, familial, global, cosmic, as it were. So when you think about the future, I'm curious, on one hand, what is keeping you up the most at night? Where are you struggling, like to feel, to push past disillusionment, or maybe even you're feeling a bit cynical or pessimistic as you're looking to the future? And then on the flip side of that, so that we can end on a slightly more positive note, where are you finding your optimism and your hope? What are you like genuinely looking forward to?
That's a really good question. I think I'm going to focus on, I'd say, a 100 to 200 year time scale. When you say the
Love
future,
it.
that's
Okay.
kind of the time scale that my brain goes to, which I know for a lot of people is like a very long time scale because it's beyond the span of my proposed life. But I think one of the things I'm struggling with that is how much the decisions that we make today are going to affect those people alive in, say, 200 years. And the fact that we are not taking them into account in the way that we're using our planet, for sure. And the idea of escaping to another planet just so that we can be bad on this one doesn't really satisfy me in that sense.
It's like we can't even figure out how to terraform this one. How are we going to terraform another planet? It's just the worst proposition. I get it. I get that it's hopeful and whatever and stars in the eyes, but it's like, come on, we got to fix this.
Yeah. If you had this one perfect, then do the other one.
Right.
But I think what makes me hopeful, though, and it is really something that I took away and have had reflected back to me about even the stories in my book. And so one of the things that I really learned through working through this book is just how powerful we are when we actually work together and when we bring together our different skills and talents and perspectives to solve problems that are greater than ourselves. And the story, as esoteric as it is, the story of particle physics shows us how we can do that across international borders, across disciplinary boundaries, to really go beyond what individuals and even nations are individually capable of. And so that in itself gives me hope for the future, that if we can just learn how to actually work together, properly together, not just, a few people in a think tank, then I think we can solve these challenges that lay ahead of us. But that is, that requires us to better understand that human force of nature of working together.
Absolutely. Well, gosh, everyone, the book is The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Changed the World. Suzie, thank you so much for being here with us.
Thank you. It's been lovely.
Absolutely. I've learned so much. It was such a wonderful chat. And everybody, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.